The weight inside of the tyre, so it's heavier. Yeah.
Isn't it nice when things just work?
I've been working on it since the very beginning. It was the test. I put it on video like 4 or 5 months ago, so it's been quite a long job for commercial.
So how long have you been working on this job?
6 years, 6, 7, I can't remember.
Our first pre-production cars that hand built, they wanted to smash them up, they wanted to take them apart, they wanted to look a bit in detail, look at all the components that made up this fantastic product.
We've had about 4.5 months of working in studios where they set different bits of car up. We obviously didn't want all the pieces just to be knocking into each other. There had to be the cleverness of the ingenuity of the piece was very, very important. So we've seen actually a lot of other ideas along the way to the final film.
Taken 1 month in script approval, 2 months in concept drawings, and 4 months in development and testing.
Generally speaking, we've been 8 of us working non-stop on this chain reaction, and with different sensibilities. There's a sculptor, a photographer, special effects technicians from the cinema.
On the day, you're talking about a large crane. You're talking about 3 people operating that crane. You're talking about 3 people operating the camera. You're talking about the perfect lighting, and you're talking about our friends, the parts, doing exactly what they're supposed to do.
Obviously, the director has this perfect take in his head, and that's the battle. That's what they're trying to get on film.
Take 50. Take 606.
To go, or something like that.
That's the only difference with software engineering. There's no champagne in software engineering.
I would love to have always commercial like that. It's more funny.
We're pretty damn sure that we've got a 2-minute tape that works.
No, sorry, Paradreams there. Sorry, not.
This microphone had an excellent lunch. So should I start? Do you think I should? Yeah? Okay. So this may not be interesting to everybody. I'm going to be showing you the inside of the COG VM and focusing on the code generator, the part of it that deals with actually generating machine code and mapping from bytecode to machine code. And I suppose my aim in doing this is to encourage one or two of you to have a go at trying to port this to a different architecture. Right now the back end is x86 specific, and maybe some of you would like to see that it's kind of easy to port to an ARM or a PowerPC or Spark or anything else. So it's going to be very dry and interior, and I'll speak a bit about the rationale for the VM and the VM in general, and then I'm going to dive down. And please feel free to stop me at any time and ask questions. And I prepared for your talk, Gerardo, but I haven't prepared much for this.
Can you make the fonts bigger?
I can do this when I have to. So when I want you to see things, I'll let you. But right now, you can suffer. So, please adjust the fonts for me, shout. So you can't see that, or you want me to go back, or whatever. So we'll make this interactive. I've kind of only done this interactively, usually with one person sitting here with me. So now you're all sitting right next to me, okay? Because it's the only way I can do this. So we'll see how it goes. COG is a faster VM for Squeak, but it depends a lot on my experience with the VisualWorks VM. And I was lucky enough to make that faster in the late 90s and had a lot of experience in that VM, and that's a C VM. And working in C is very, very different. It's very slow and frustrating. It's difficult to get code through the compiler. There's no scriptability. Running experiments in the context of the JIT to find out what your next policy decision should be can be very, very difficult, you know. And this is in slang, and this what's slang? Slang is two things. One is that it's just a smalltalk program. The virtual machine is a smalltalk program, and we can execute it. So if I start it up, there it is, loading the image. Oh yeah, I got to disable this breakpoint. Hang on, let me find out where that breakpoint is. And if I started off going, you know, in this window here, eventually will appear some Squeak windows, and this is a 3.9 derived Squeak image, and it just executes much slower than the real thing, but it's usable for development, and so you're using the standard Smalltalk development system, and it's fun, and you can code on the fly, which is a major departure. So just get rid of these guys. Now, of course, I have to remember to zoom out. But One of the things that's very different from VisualWorks is that this first code generator is quite naive. The code generator in VisualWorks was quite a sophisticated one by comparison to this. And the reason for my having done a simple generator is that my current employer, Teleplace, wanted achievable results sooner. So rather than wait a long time for something excellent, they would rather have incremental deployment. So COG has come in 2 phases, and there are more planned. In the first one was, I suppose, 3 phases. The first one was to re-implement the image level compiler to use closures, because closures now mean that execution obeys stack discipline. When you're using the old block context, I don't know if you know this, but before closures, creating a block created a stack activation, an activation record. So when you invoke a block before closures, what you're doing is inserting an activation record out of order, right? One that you created long before, and returning from it. And that makes, when you're mapping that execution model to machine code, it makes using call instructions difficult, because blocks, they have their stack associated with them. You have to invoke them in some special way. So the first stage was to re-implement the compiler and introduce closures, which gives you a stack discipline of activation, and some other details to do with closed over variables and how those are accessed. And then the second stage was to take the standard Squeak VM and make it faster by mapping contexts to stack, and just doing the part that is an enabler for later doing machine code. So there is an interpreter in here which is known as the stack interpreter, which instead of allocating a context every time you activate a message, grows a stack down. And so activation return looks conventional. And in order to deal with the fact that you have context objects, you can associate a stack frame with a context. It's called marrying. And then when the stack leaves, they get widowed. And there's also a divorce process. It's great. It's very familial. And that is a reasonably complicated optimization, but it still has effect within the standard VM, so that the stack interpreter, John McIntosh running graphics code on the iPhone found that the stack interpreter is twice as fast at doing graphics as the existing VM. So it's significant. But when we add a JIT and some sophisticated inline caching, we can get to significantly faster than that. I have benchmarks that are 5 times faster in this VM than the original one. And in Teleplace, our experience, Teleplace's product is a 3D virtual world for business communication. And using COG, given that the system is obviously spending a lot of its time doing real work, like drawing frames, etc., is that our frame rate increased by a factor of 3. So the COG VM is providing a speed up of 3 in a real application. Okay, so the reason why the code generator is naive is to get it delivered quickly. And by naive, I mean that every bytecode in the source language, and the source language of the JIT is the bytecode that the VM executes, because we translate from this bytecode, which is our source language, into machine code. And what's going on in this code generator is the naive thing that every time we...
Zoom in.
Yes, of course, thank you. Jesus, eventually you'll only have to tap your head. That's right, sorry. That's right. So we'll come back to this method, so we should become familiar with this guy. So every time we see a bytecode that pushes something onto the stack, that translates into machine code, which pushes something onto the stack. So when you get to this send less than consumes two arguments. The first one is the receiver and the second one is the argument, and returns a Boolean. This actually pushes a Boolean on the stack. So it takes two things off the stack and pushes a Boolean. Consequently, this jump false has to synthesize the constant true and compare, and synthesize the constant false and compare, and if it's neither true nor false, generate a runtime error. Whereas the code generator in the VisualWorks VM defers the generation of code until it consumes operands. So we don't generate the code when we push the temporary. We generate the code when we send the less than. And it's easy to look ahead and see that it's followed by a jump false and generate two paths, one of which is message sending, and one of which says if these two arguments are tagged integers, do a comparison and jump on the condition codes. So there we avoid reifying the true object and the false object, and we've done a comparison with a machine instruction. So that's the basic difference between COG and VisualWorks, and the reason why if you run an if to a to-do loop in VisualWorks, you'll find out that it's significantly faster than COG. It's 2-3 times faster. And so there's still this potential for COG to go faster, and that's work that we're going to do. So in all of this, I'm not pretending that this is a sophisticated code generator, but I do think it's a simple code generator. So let's start this thing running and put this breakpoint back in. So one of the things with object-oriented languages is that, and with an image-based Smalltalk, is that in startup you quite often run large methods which don't do much. They do some initializations, and if you are going to compile them to machine code, you get significant expansion because there's a lot more machine code than this compact byte language. And if you're only going to execute it once, it's less efficient. You've spent all of this time converting it into machine code, which was slower than interpreting it in the first place. So one thing that's good is to have a policy which defers compilation. And so one of the main differences here to VisualWorks is that this is both an interpreter and a JIT. And so it interprets, and it only JITs code if a method is reused. So the first time you look up a method, you find it, you put it in the method lookup cache, and you interpret it. Every time you find the method in the lookup cache, you ask, is it small enough? Which is asking how many literals there are in the method. That's the default policy. And then compiling it to machine code. So what we're seeing here is a few things.
So if I understood correctly, you compile to machine code, and the second time,
yes,
it's already in the cache.
Yes. So let's have a look. So here we've got a simulated VM, and it's in its simulated dispatch loop. This is no good. Let's pull this down. Let's see what we've got. No. Why did it do that? Okay. Yeah, this is going to work poorly, but we'll see what we can do. I see. Right, now I got it. So,
just to make sure, so just focus on the branches, right? On the if.
No, I will come to that. Right. So what's happening here is here's the actual code for a particular bytecode that encodes for a particular send, and the interpreter collects the message selector and sets the number of arguments and finds the receiver. In this case, it's 1 down on the stack because this is a 1-argument bytecode. And then we find the lookup class and call common send, which all of the send bytecodes go into. And so what does common send does? It has some boilerplate which we're not interested in, and then it looks up the method and tries to execute it. So here's this is a simulated sort of a debug hook. This is the real one. So it looks it up in the method lookup cache, and if it found it, then it says, if it's appropriate, compile it to native code. I have a verbose disease. My selectors are 10 times longer than they need be, so I apologize for this verbosity. So here we are, and it's saying, okay, let's check whether it's a particular size, and let's ask the JIT to compile it. So let's have a look at this method. Well, if I print it, it's the equals guy, and so it is indeed this guy that we compiled here. So where's it? Explore method. Come on. Yeah. So what we have to do, and I'm not going to concentrate on optimizations or anything like that. I'm only going to concentrate on the process of converting this to machine code. Is generate essentially an equivalent series of machine instructions which execute this without the bytecode in the middle, and with the ability to make sends go faster. But we've got some problems. Here's a jump here, and it jumps forward. So if we're doing a linear pass, one of the problems that we have to do is resolving forward jumps. Backward jumps, we've already generated the code that we're going to jump back to. So one of the things we have to do is to deal with forward jumps. Another thing that we have to do is that in this implementation of Smalltalk, the code for blocks is embedded in the middle of the code for the enclosing method. So you have a tree of blocks. And logically, the code for the outer method is here. It just creates a closure. And so we need to skip over this intermediate code because we need to generate linear code for the method. And we have to generate code for the blocks following it. So we need to tease that apart. So there's a structure in there for kind of flattening that. And then we have to generate concrete machine code. So one of the things you want to do in a JIT is not spend a lot of time compiling, because that translates into latency when you're using the interactive environment. So you want to keep the number of passes as simple as possible. And in fact, the VisualWorks JIT is a 2-pass structure. It makes 1 pass to find out what kind of method it's compiling, and then 1 pass to generate code. Whereas I actually have 3 passes. One, I make a pass to find out what kind of method, how many blocks it's got in, where the forward branches are, and then a pass to generate an abstract code. And then I make 2 passes over that abstract code, one to size the code so that I can compute branch deltas in a very naive way, because on x86 there are 2 kinds of branches. There are short branches with a byte offset plus or minus 128, and then there are long branches which are 5 bytes with an unlimited, effectively unlimited thing. And it's important for concision, for getting as much machine code in the cache as possible, to use those short branches as possible. So there's a very naive, simple spanning algorithm to allow me to generate the right branch width. So before we can do any of those passes, we also have to allocate some data structures. So there's a crude heuristic which says, okay, how many bytecodes are there in this method, and does it have a primitive, and the primitive would have to have some extra code allocated for it. And based on those heuristics, we allocate a sufficiency of memory for us to use. And in this case, we do stack allocation. So what's going on here? I have got a Smalltalk program, and it's going to run in C. So my Smalltalk program has to be translated to C, and when this VM was developed, and in fact, in general, it's still a difficult problem to map a Smalltalk program down onto some other code. So the translator from Smalltalk to C is naive and limited, and means that you cannot write rich Smalltalk control structures. You cannot use dictionaries. You cannot use anything cool. You can use to-do loops. And there's no garbage collection, because this is targeting C, and C doesn't have garbage collection. So what we do is just use arrays and map some structured types, some objects down onto C structs, and use stack allocation to avoid having to garbage collect. So what's happening now is that we're just figuring out how many bytecodes we've got, and we allocate some space. So I'm going to allocate enough space for a series of abstract opcodes, which I'm going to generate code in terms of, and space for fix-ups. Fix-ups is the branch fix-ups. And another thing that I need to do is, because I'm generating machine code for objects, is that I'm going to have object references embedded in my code. And I'm also going to have other things in my code, like send sites, that I may have to unlink if you redefine a method. You know, some sends are mapped to calls, and if you have some call to a target method, and in the IDE you redefine that, then that call has to be located and undone. So annotations are the recording of the metadata for the generated machine code. So okay, we'll generate these guys, and in C, these are all allocates. These are all stack allocations. That's way too small, isn't it? Sorry, they're stack allocations. And in the simulator, we have these objects which pretend to be C arrays. They basically do zero relative addressing for us, so that the code works when we translate it to C. So as you can see, there's all of these hacks to deal with this translation to C. But never mind, because we're still using the debugger. We can still code in the debugger. That's pretty great. Okay, so the first stage is this scan, and if you look at the way that you would write a JIT in C is that the natural way would be to have a switch statement, and for all of the bytecodes do this, and you'd immediately construct this giant method, and you'd just be led down this primrose path into writing a completely unmodular nightmare. And that's exactly what the VisualWorks JIT is. There's several pages of code, and you scroll and scroll and scroll. Instead, I've got a table-based system. So, and we've even got a hierarchy. So I have an abstract JIT, and this is the simple stack-based JIT that does the one-to-one mapping. But lying off here is a sophisticated deferred code generating one, which is a gleam in my eye right now, but will be realized. And the bytecodes are implemented as a dispatch with perform. So immediately, because we're in Smalltalk, we're using a much more modular structure. So what we're going to do is be able to plug different bytecode sets into the JIT just by redefining the table, instead of having that horrible thing. And I look at Gilad at this point, because he looks skeptically back at me. It's not happened yet. It will never happen, he said. He's probably right. And so you can see that there's some metadata associated with these generators. So frameless is an interesting word. One of the optimizations that the JIT does is, if the method is simple, it's just an accessor and it doesn't actually do anything, just returns a constant or whatever, we don't actually need to build a stack frame for it. We can just execute the code as a leaf. So one of the pieces of metadata is, does this bytecode need a frame? Another is, does this bytecode return? And if you were in a block, if you were executing in a block, would this actually require a frame in a block? Because method and block activations differ. I don't want to say more.
You only have one bytecode that requires a frame. If it's frameful, you do full frames.
That's right, exactly. All you have to do is have one bytecode that says I need a frame, and you have to spit out the frame. Exactly.
Does this, or another similar, this one support perform?
Yes. So you do it in a horrible hack where you pass these tables to the code generator. So the code. No. Yes. So that those tables will get mapped to a table of function pointers.
Oh,
okay. So right. It's not so bad. And then perform is just mapped into function application. And we'll see that. Okay. I can't find my windows. So this basically abstracts the generator for each bytecode. So here we fetched the memory byte. We need to be bigger. We fetched a byte from the method, and we find the generator. So if we do this in C, you can't do this in C. So okay, this is the gen push temporary variable bytecode. So we are indeed in this first method. So what this does is simply work out where the blocks are and defer scanning the blocks, so it linearizes the blocks. It removes the tree structure and makes everything linear. And then it computes branches and makes sure that if we are a backward branch, we have a target. Because as we generate the forward branches, we can construct a label object. So there's a parallel array of labels next to the code, next to the bytecodes, and we can match bytecode PC to label in this array of labels that we collect for. So that's the first pass. It constructs a number of descriptors for blocks and gives us backward branch labels, etc. That's right. So let's step over that. So then we need to actually compile. So this method has a frame. So we're going to we can look at understand compile prologue and compile entry tomorrow. I don't think I need to explain that today, but the entry point is essentially the dynamic dispatch checking, efficient dynamic dispatch checking that checks that it's valid to get into the method. And compiling frame build is doing something that's very similar to what's inside these generators. So I'm just going to go straight to the generator rather than go into that. So okay, to compile a method body, we need to compile. Right. So to compile the method, we need to compile the abstract instructions for the method, and then later on we need to compile the abstract instructions for each block. Okay, so this doesn't have a block in it, this method, so we're just going to look at compiling the abstract instructions. So here's the dispatch loop. We grab the first byte, which is the bytecode. So and then the descriptor for it, and then the descriptor tells me how many bytes that bytecode has, and then depending on how many bytes we collect the other bytes, and then we just do which we store in instance variables, and then we do the perform, which in C is indeed a function application. So here we're going to generate push temporary variable, and we're going to find out the index of the temporary variable from the first byte. So the byte code, the first 16 bytes code for 0 through 15. So now we go into something that looks very much like assembler. And this is, I guess, the core of the thing, how this simple mapping goes. So there's several things to look at here. One is that the JIT is our assembler. We have selectors which look a lot like assembler instructions. And they correspond to the instructions for an abstract to-address machine. So this is not Spark, where you have register gets, register op, register. It's simpler than that, but you could extend it. And you might extend it if you wanted particularly efficient integer arithmetic. But for the most of code generation, a to-address machine is fine.
What's the class of the receiver for that method?
So that's a simple stack-based cojit. So it's this naive JIT. Now, there are a number of other classes in there. So remind me to come back to what classes I map to. So I guess as we move down, we'll start to have a look at some of the struct classes and things like that. Is this too loud, or the sound is good? Great. So let's have a look at this abstract machine. So there's a namespace here called cog register transfer level opcodes, and it's got an initializer. Right, here we go. And there's kind of a simple series of conventions, which is that R means a register and RD means a double precision register. CQ means a constant which the machine is free to pack in as few bytes as possible, and CW is a constant which must have a particular size. Because we're generating code for Smalltalk and we need to update that code on the fly, we may do things like have a constant load which is actually loading the address of an object. So let's say that we're synthesizing the object true, right? That will actually be a machine code instruction which will be, register gets some constant. And the garbage collector may move that guy. So later on, you may come back and try and modify that instruction with a different value. So you have to specify that certain values are in a constant width, the full width of the machine, because if there's some tricky encoding, it may apply only to one range of values. So we distinguish between quick constants, which are immovable, which we use for immovable values, and for word constants that we have to maintain. So then the other things are, do we have an address? Do we have a memory word? So this is very much like a simple CISC. A memory word, MWR, means we're talking about 32 or 64 bits in memory, where we've got a register containing the address of that word. And then there's just a very simple set of instructions. So there's a label, there's some pseudo-ops, a label, an alignment to a boundary, a no-op, etc. And then there's a call instruction, a return, a jump. There's a series of conditional jumps. There's a series of floating point conditional jumps. And then there's data movement. Move register to register, move from the word at an absolute address into a register, and so on. And then there's some logical shifts, some comparisons, and that's it. And then there's a great piece of introspective code here, which says, how many class variables have I got? I've got to give each an integer code. So you can't do that in C. It looks at the method and it figures out what numbers to give all of these, and in the class pool gives them values. So these guys get automatically mapped to integer codes. So that's the way that you do enums in Smalltalk. So the instruction set is then realized here as a whole series of methods, each corresponding to those, and they generate an abstract instruction with the code for the instruction plus some number of operands. So you can right now I need up to 3 operand. So we tell the generator to use specific types by using pragmas. So by default, everything's an int. And then if you need pointers, you have to insert these pragmas that say, for example, the abstract instruction is of type abstract instruction. And then the code generator needs to know the type of a variable so that it can map these message sends not onto procedure calls but onto struct dereferences. So there's a very simple thing in the code generator which it knows which types are structs. So let's take a look at an abstract instruction. I think I've got that here. So an abstract instruction is just a smalltalk object. And what I'm doing is a 2-pass structure where I'm going to build up a set of these abstract instructions, and in each abstract instruction there's an array of bytes into which I'm going to generate its machine code eventually, and then I'm going to concatenate all of that machine code. Instead of generating the machine code in one go, if you generate the machine code in one go, generating jumps is really awful because you have to kind of know where you're going to jump to. If you're generating machine code in the first time, as you know, right? You live that hell. That's right. That's right. So instead, we have we have this 2-stage thing where we assemble the abstract instructions and then we concretize them. So this thing needs to get mapped to C. So it gets mapped to C. Each of these struct things has like a method which for certain names maps them to particular types, and then when we generate the VM, generates this type. So that's just a direct translation. We've got an opcode, which is the integer code of the abstract instruction. We've got the number of bytes of machine code that this guy has. We've got its maximum size so that we can do this branch stuff. And then we've got the actual machine code that we're going to concretize. And then we've got those abstract operands. As we concretize, this instruction will gain an address in memory, which is its target if we want to jump to it, right? And we may have a series of instructions which are dependent on this instruction, which are basically the instructions which are jumping to it that need to be fixed up to come to this instruction. So there's a simple mapping of certain of the class types, classes in the VM, these flat objects which map to structs, right? And they're just containers.
Eliot, you said that you have to perform a second pass to fix the jumps, but is only that? Why a second pass and not just something simpler to fix?
So the first thing is with this abstract concrete thing, it's very easy to insert labels to, the structure is easy to play with, but it means that you can't generate a jump except to an abstract instruction. So it's not until you push out the machine code or assign addresses that you can actually generate that instruction. So I think that's just more flexible and more are more fun to play with. But the real thing is that I have this anal thing to do with I don't want to generate big branches. I mean, my friend David, what he does is he always generates big branches. But if you look at the Prolog code, you're talking about adding 30% to that code, right? So I think it's really important to try and produce small, compact code. You get better cache performance, and so I'm willing to pay this little bit of complexity for that. Right? And maybe I didn't think through the trade-offs, but it works for me, so I don't care. At a meta point, because this is like my third significant VM, fourth VM that I've worked on. One of the things that's really lovely is to know what you're doing, right? I mean, I don't, trying to keep it as simple as possible, and I'm in a very lucky position. Most people program in a situation where they're trying to explore this unknown domain. But I was lucky enough to, do this for a third time and really think how I could keep it as simple and comprehensible to me. And so a lot of this is kind of idiomatic. This is a reaction to my experience with visual works and a memory of what I did with my first brouhaha JIT. Right? And so I didn't really do science. I really didn't sit down and do a lot of measurement. It kind of flowed, and that's self-indulgent, but it's 3 times faster for frame rate, so it worked. So I'm getting away with it. But,
Do you also, when you're creating a block closure, you need to know the address of the first instruction of the block closure, and that's also forward reference, right?
Yeah, so
the same structure.
We use a tree-like dispatch. Right. So what's the problem with block dispatch? What Richie is talking about is you've got machine code, and some of that machine code is for a block, and then you have a block closure. Well, when you have a block closure, when you have a block closure in your hand, you don't have a machine code PC, you have a bytecode PC, right? So, yes, you could, under the covers, try and know what block closure was and allocate an instance variable and fix up that instance variable when you reclaimed code and threw away their block. That's a nightmare. So instead, the very simple thing is that most methods will have at most one block in them. And those big methods that have huge numbers of blocks in them are unlikely to be performance critical. So you just create a binary tree which compares the bytecode PC against constants and jumps to them. Yeah, so it's very simple. And mostly you're doing 2 comparisons. And the other thing that's really important, what's changed in terms of machine behavior, let me just finish my point, since the first Smalltalk JITs were built in the early 80s, and Self was worked on in the 90s, is that we now have instruction fetch units, and we have sophisticated handling of call and return. In x86, basically a call instruction informs the branch prediction logic for return instructions and the prefetch, so that when you come to execute the return, it's already fetched the instructions. So whereas in 1980, there was a huge difference between a call and a jump, there isn't any difference in performance between a call and a jump now. And so I spent time in the 90s trying to do micro-optimizations in visual works where, for example, accessing a global variable in machine code would try and flatten that, which would be a send and a call, into some jumps that would say, if it's of class variable binding, just index. And there was no difference in performance because of the prefetch. In that block dispatch, once you've got this value in a register, that's what you've paid for. You pay for the read. The instructions to do the comparing against the constants and the jumps to the target are essentially free, right? You'll get a store when you read that instance variable, but the fact that you've got slightly larger code there is not important. So, you really have to hold that in mind when you're architecting performant code, because that will really save you, right? Calls are cheap, only reads, are expensive, and believe it or not, writes are cheaper than reads because the processor can schedule the write and not block on the write. Right? There's a very interesting thing in the current hotspot VM where to implement the breakout from Java to go to poll for events, exactly that problem we were talking about yesterday with the heartbeat. The way that they do it is in the prologue of their generated method, if the hardware supports it, there is a write to a page, and they unmap the page when they want to break out, so that write creates a page fault, and that breaks them out, because they don't pay anything for the write. So when the page is in memory, the write is effectively the same cost as a no-op, and so the write will happen sometime after we've executed all of the code. It's cool. So, okay, so yeah, so that's blocks is this tree dispatch. So okay, these abstract instructions, it's just a Smalltalk object, but it gets mapped into this struct, right? And we've stack allocated an array of these structs depending on how big the method was. So we don't have to do any dynamic resizing. We just always allocate too many. So let's construct two of these things, and then I can, let me inspect one of them. I'm getting used to this now. All right. Another nice thing in Smalltalk is that you can put effort into these guys printing themselves nicely, which is great. And because it's an incremental programming environment, you get immediate gratification. You see some print statement, it doesn't tell you anything. You spend 2 minutes writing a print statement, immediately you have it. So there's all of this amplifying feedback doing incremental development, which I think produces a qualitatively a better experience. So okay, so this instruction that we just created, move into a memory, from a memory word indexed by a particular register into a temp, is mapped into, there's a particular code which we can map back into a class variable name to print it. We haven't generated any information as to the amount of machine code yet. And here's the array for the instruction, and here are the operands, which are all getting mapped to numbers. There's the simple convention, if it's a number or an address of an object in the heap, it's that value, and then negative numbers are registers, and so these code for registers. So what is the register model? So the register model is taken from Peter Deutsch's VisualWorks VM. It's a very clever observation that Smalltalk methods are typically small. Here's a tiny typical method. We've got 3 sends. There's no basic block of any size here. There's no profit to be had from doing a great job of register allocation here. So instead, we don't try and do any kind of register allocation except for the high dynamic frequency operation, which is sends. We're doing sends all the time. So what we want to do is to get as many variables which are involved in sends in registers as possible. So the register model, going back to this guy, and it's kind of defined by the most stunted processor on the planet, which has 8 registers. So there's a floating point register and a frame pointer register and a stack pointer register, and then we'll have the receiver of a message send and the result in a register. We'll have a temporary register which we can use for various things. There's a class register which is used for making sends go fast. And then there's a scratch register, which we also use to hold, and you will recognize this, we also use to hold the argument count for sends that have many, many arguments. If you've got more than 2 arguments, we need an argument count in a register. And then I'm not using these yet, but for primitives to go fast, we've got 2 argument registers, where if we were going to compile the @put method, what we want to do is all of @put needs to be in machine code. So that's the receiver, the index, and the value. We'd like to be in registers. So the code generator doesn't do anything clever with register allocation. It does this fixed mapping. It has a fixed set of registers, and they are mapped in a completely fixed way down onto the available register set. So if you're going to port to ARM, you just choose 8 registers that are available and map direct to them.
So you do use 2 registers for arguments for the receiver?
Yes, it's there, but this simple code generator doesn't yet target them. But it will do when I do the deferred code generation. Yeah. Okay. So now we need to...
Back to that question.
Yeah.
I was a bit surprised that are you using like a binary tree for blocks? So you go, oh, if it's this address that way, and if this address that way, etc.
And I beat VisualWorks because VisualWorks does a hash lookup of a hash table. Because most of the time, methods have 1 block. And if you have 1 block, you don't even have to test. If you have 2 blocks, I only have to do 1 test. And the number of tests grows as the log, and that's why block dispatch is faster in COG than in VisualWorks.
That's wonderful. It was not my question.
Okay.
So, also in VisualWorks, while we're at it, binary search was used to look up methods in method dictionaries, because there, method dictionaries are, as you know, sorted collections of pairs of selector compartments.
Is this germane to the talk or about hashing?
No, I'm not.
Okay.
And the interesting thing was that still an article published 3 or so claiming that linear search beats binary search for up to 64 entries.
Wow.
It is still applied. I mean, I measured, and it still wins. So I made it so that linear search is used for up to 64 entries. Now, with binary search, and
no, this is a different thing. This is a different thing. We're not looking through a table of values to find matching values. The problem with method lookup is to find the index of a method given the selector. Here, the problem is to find the target PC for a value. Right? So
you're mapping from what to what? So that's what I don't understand.
So well, let me show you the code. We'll come back to that, and I'll show you an example. Okay? Because it's not important now.
Yes.
Where are we? So let's skip through then to generating the code. So you can see that what's going to happen for each bytecode is that we're going to generate some number of these abstract instructions. So we can step forward.
Eliot,
Yeah.
you have 5 minutes.
Oh God. Okay. Right. Oh yeah, and I forgot. Now I can't disprove you because I forgot to start my. I think okay. So now we have to generate the machine code. The first thing to do is to be able to know how much machine code, so that we can know can we use short branches or not. So we need to know the size of each instruction. So there's just this huge method. Which gets mapped to an opcode. So for a particular processor, you need to decide how you're going to map each of these abstract instructions to machine code, and to know how much machine code you're going to generate for each instruction. So after this pass, we know the maximum sizes of these instructions. Some of the instructions we may be able to encode in shorter, but at least we know, and so we know the maximal distance. And so if we can do a short jump over a maximal distance, providing we always generate the same jump once we make our choice, we stick to it. We can generate small jumps, because if it's small when it's large, it's going to be small when it's small. But we can't do the small number of jumps which it would have been small when we shrunk down. We give that up. So once we've got the maximum sizes, we can then go into a loop where we can allocate an amount of memory now because we have a maximum size, or rather we can start with a start address. We know where we're jitting to. We're like jitting method here and then there. We just chomp through memory. So we know the start address at which we're going to generate instructions to. We just go through a very simple loop where now we have the addresses of these instructions, and we can size a particular instruction, and then we can find the address of the subsequent instruction. And once we've done all that, we can then where does it fix up jumps? That's right. And so as part of this process here, we have remembered whether an instruction needs a fix-up operation, and we can perform these things. So let me just show you what a concretize looks like. And so again, that's just a huge case statement. And if I have a look at one of these, let's have a look at the call instruction, for example. That now just looks like, let's punch out some machine code. And so, on x86, it's E8 and then 4 bytes. Okay, so it's very, very simple, and it's table based. And so, if you have an ARM, you have to decide these mappings and fill in these. So it's not a lot of work to do. So once we've done that, we've got all of these instructions with the machine code in them, and now we can allocate one more thing. I should show you that. Let me show you an example of that. So for the garbage collector, to allow us to embed stuff in machine code, we need these annotations. And so we've got some very simple types of annotations. We have about 5 different annotations. And so we build up a set of annotations that we need then to associate with the method. So just remember that, and I'll come back and show you what that looks like. So now we know how much metadata, how much machine code we can allocate a method. Oh, I can't step at the same time. This is agony. Allocate the method, and then output the instructions, and just read from that machine code into the stuff, and then generate the metadata, which I'll come back to. We'll look at it in the inspector, and then fill in a method header, which I'll look at, and then we're done. So we've now produced some method, and another weirdness is that we can't use a normal Smalltalk object for this compiled method, because it actually lives in the byte array in our simulated heap. So I have to have an object for the simulator, which is a surrogate, which knows that its object is actually bytes in memory. So this is a mirror for a compiled method thing. And so I've got this thing has exactly the same API as the simulator's notion of a method. So let's.
Eliot, I'm sorry, but I must invite you.
Yeah. Okay. Can I just show you one thing, right? Because we had a late lunch. I just want to show you. Just inspect this method and take a run through the machine code. Okay. So 5 minutes, please. So here's the machine code that we've generated, and here's a header, which is basically telling us how much machine code we've got and what's the compiled method that we're associated with, so that we can map between the two. And the way that we map to this method is that in the Smalltalk object, its header word is replaced by the address of the JIT, and so the header word is here. That's the actual header of the compiled method that we've replaced. So we've got this direct link from the object, Smalltalk method object, and its JITted dual. So one of the beautiful things about a Smalltalk VM being that it's well designed is that the interface to methods and to context is more or less object oriented. There are very few places in the system where you access that state. So it's very easy to change the accessor for compiled method to say, if my header word looks like an address, I actually get my header from here. Right? So, okay, and then we've got lots of machine code that we generated. Now, I want you to draw your attention to all of these annotations in the machine code. So this is part of the prologue code, and what we're doing here is building a frame, and we're pushing the address of this JITted method object. Well, we use a fixed space, JITted space, and we may reclaim some of these methods. Some of these methods may get redefined. We may throw them away, and we may have to compact the zone. So method addresses need to change. So we need metadata that tells us where method addresses are so that we can fix them up on compaction. We have objects. This is the nil object. When we build a frame, we have to initialize all temporary variables with nil. So we need to know where object references are so that when the garbage collector runs, it can fix them up because the garbage collector can move them. Then there are places where we need to map back from a machine code address into the bytecode PC so that the debugger still works. So wherever there's a point where we can map back, if there isn't already metadata for that, because we know we have to do it for sends, but there are other points, we have metadata, and so by parsing this method with a counter, we can compute the bytecode address for each thing there. And then so here's a send that's been generated, and we'll see more detail about that tomorrow in inline caching. So what happens is that the metadata is generated at the end of the method as a series of bytes. Very, very simple. So this one's got 12 bytes. And the way that it works is that each of these is kind of like a 3-bit tag and a 5-bit displacement. The 3-bit tag gives us what the annotation is, and the 5 bits gives us the distance to the next annotation. So we just run through this thing, going through the machine code, and it labels machine code addresses. And we're able then to garbage collect object references, redo sends, and map from machine code PCs to PCs.
So you have to change your GC to follow these annotations?
Yeah, so both the GC has, in the JIT, there's an extra call, which is to traverse over machine code. There's also the observation that if you've got, some large amount of machine code, you probably don't want to waste time scanning that in an incremental collection. So there is a list of methods at the top of the zone, which are those methods that contain new object references. Those methods that contain references to objects that are in the younger generation. And so in a normal image, there aren't any. So you never end up running the garbage collector over this. It's only when you're compiling methods on the fly. When you load a Monticello package and start executing that code, you may have created new symbols, etc., etc., etc. Right? So most of the time, the garbage collector doesn't even visit this, but the metadata must be there. Okay.
So GDIT code is stored in byte arrays.
It's not even a byte array. It's like at startup when we allocate the heap. There's a value in the image header which says how much machine code to provide. We just allocate a fixed size, and then you can vary that. There's a VM parameter at value which allows you to say, and by default it's 1 megabyte, and it can grow from there. Yeah. So okay, any more questions?
Sure there are many.
Well, yeah, okay, yeah. I can show you the block dispatch.
One question, maybe very combining to machine code takes time.
This is very quick, right? I mean, you saw how simple and naive each of those passes was, and all of the things which take time in a C compiler, register allocation, optimization. I'm not doing it. Right? There's 4 loops in this, and they're all loops that they all just go in a single pass. So there are no recursive operations. There are no nested loops.
There is no need, because I was thinking like maybe I want to deploy an application, I can run before the beta.
Okay.
Discover us.
Okay. It does not take measurable time in the JIT. If you were to profile this, you might see 1%, 2% of entire execution time in startup going into code generation, but you wouldn't see more. So that optimization doesn't get you anything except a huge amount of machine code, because the expansion from bytecode to machine code is of the order of a factor of 10 or 20. So I wouldn't waste time in doing that. In fact, you probably get better performance by only compiling the working set and having that in the cache than compiling your entire application to machine code and having poor code density. So I believe JIT still makes sense. Right.
Sorry.
What happens if you run out of
Right, which you do, because it's finite. So at that stage, the system goes through all of the existing methods, makes one pass where it kind of counts how often methods are used, and then it chooses to throw away a third of those methods, just throws them away, compacts it down, and continues. No, 1 megabyte is not enough. It will do at least one code reclamation on startup typically, but that code reclamation might take a millisecond, 2 milliseconds. It's tiny. You don't see it. It's of the cost of a garbage collection. Maybe it makes sense. Yeah, I mean, you can experiment by all means. Make it 16 megabytes. See what it works. But I find tuning my heap is much more important than providing more code memory. I basically don't see the cost. A megabyte seems fine. We run a megabyte in production. We run much bigger, younger generations. We spend much more memory on the heap than we do on the generated code, and we never see performance issues from that. And we have a good profiler, which really does tell us what's going on. Yeah.
Okay.
Sorry.
Thank you very much. Okay, so at 4 we start. We are half an hour question. 10 minutes. At 4. At 4 we start the next session. Okay. The break.